Okay, we're going to combine the things that we've learned in the last couple of videos into one final lesson, kind of a master class, if you will, of biology mathematics. We're going to be combining both our Hardy-Weinberg analysis, which allows us to figure out the gene pool of a population. And we're going to use a chi-square analysis to determine if a population is in equilibrium. In fact, we would call it Hardy-Weinberg equilibrium, or if perhaps it is evolving over time. If the gene pool is changing, that is one way of describing evolution, that the gene pool is altering over time. So let's take a look. We might say that a population is in equilibrium when its gene pool is sort of settled. That is to say that the values of P and Q from one time period are the same as the values from another. If we apply that thinking to our last example, when we examined the population of plants, we found that the probability of finding of inheriting little t from a parent was 0.447. The probability of big T was 0.553. So P was 0.553, Q was 0.447. If the population's in Hardy-Weinberg equilibrium, then we should find phenotype distributions that correspond to these genotypes, this gene pool or allele frequency. So we're going to imagine that we return to this field 2 years later, look at the same population, and examine the phenotypes. So we do that, and let's do it a piece at a time here. So suppose we return 2 years later, and we find a bunch of tall plants and a smaller number of short ones for a total of 872 plants. We have no reasonable expectation to expect there'll be exactly the same number of plants as before, so we're really looking at the ratios, how frequently things show up. Okay, so what were we expecting? Well, that's a big question in the Hardy-Weinberg analysis, right? We need to know our expectations. Well, from what we established earlier, we knew from the previous gene pool that 20% of the population should be short, and of course 80% of the population should be tall. When we apply 80% to 872 and 20% to 872, we get close to 700 tall ones that we expected and 174 short ones. What did we observe? Well, we observed this, 627 and 245. Lower, but is it too low? Is it so low that we would have to reject the idea that the gene pool is settled? So let's take a look at that. Each of these contributes to a chi-square number, right? The difference here is the observed minus the expected, which gets squared and divided by the expected value of 698. So the tall plants contribute a value of 7.22. Short plants, we do a similar calculation, divide by 174, and get a number like 29. And, if your spidey sense is tingling, that's a pretty big number. I think we're going to find that this is a gene pool that is in transition. Our overall chi-squared number, however, is the sum of these two things. So we have a chi-squared number of 36.2. So that seems big, but let's go and be diligent and take a look at our table. There's only two outcomes, tall and short, so there's 1 degree of freedom. So we look right here in this column, and of course 36.2 is well beyond either of these two numbers here. So we could probably extend this table mathematically to 0.001, 0.0001, and so on, but it's not important. At least in AP biology, there's only these two levels of discrimination that we might apply. And so here's what we can say. In this particular case, we can say with 99% confidence that this gene pool is different than it was 2 years earlier. These observations that we made 2 years later are not just random variations around an expected outcome. We might be able to say with some real confidence that this is a population that is truly evolving. The gene pool is clearly different than it was 2 years ago. There's a lot more, many more examples one could play out with this, but I think now we've got super examples hopefully clear examples of Hardy-Weinberg problems, chi-squared problems, and combinations of Hardy-Weinberg with chi-squared analysis. I hope you found that to be helpful, and come see me if you would like to discuss any of this. Take care.